everyone, we're continuing today with section 2, solving using trigonometric ratios. So in section 9.1 we covered at the very end Sohcahtoa, meaning sine is equal to the opposite side over the hypotenuse, cosine is equal to the adjacent side over the hypotenuse, and tangent is equal to the opposite side over the adjacent side. Now we're going to use that to do some solving. So in example 1 here, it says write each trigonometric ratio as a fraction and decimal rounded to the nearest hundredth. And what you need to know here is for this whole unit, and as we've been doing for the rest of this class, anytime you're given a decimal place, you're going to round to 2 decimal points. So the sine of angle J is going to be equal to the opposite side over the hypotenuse. That's 60 over 61. If you use your calculator to divide out 60 over 61, it's going to be rounded to the decimal point 98. Now we want the cosine of angle J. The cosine of angle J is the adjacent side, that's Ka from Sohcahtoa, adjacent over hypotenuse. So I have 11 over 61. 11 over 61, when I divide that out, gives me about 0.18. Then we want to do the tangent of angle K. And tangent is opposite over adjacent, toa. Opposite over adjacent. So I have 11 over 60. 11 over 60, if we divide that out, gives me, again, 0.18. And that is, again, rounding. So this is 11 over 61 and 11 over 60. They are really close and they happen to round to the same decimal. That's not always going to happen, but in this case it does. All right, next we have the sine of angle K. And the sine of angle K, so that's opposite over hypotenuse. So that'd be 11 over 61, which we already have that fraction written down above on our page. So that is, again, 0.18. All right. Example 2, same thing, but now we have a new fraction here. So we have the cosine of angle A, which is off the screen here. Angle A, cosine, Ka, adjacent over hypotenuse. So I have adjacent, which is 24, over my hypotenuse, which is 25. And again, the hypotenuse is the longest side, which is opposite the 90-degree angle. So I have 24 over 25, and that simplifies to 0.96 as a decimal. All right, next we have the sine of angle B. Sine of B is opposite over hypotenuse, so I again have 24 over 25. And we already know that that is 0.96 as a decimal. Then we have tangent of angle A. Tangent is opposite over adjacent, again, not the hypotenuse. So I have 7 over 24. 7 over 24, when I divide that out, gives me 0.29. Then I have the cosine of angle B. Cosine is Ka, adjacent over hypotenuse. So I have 7 over 25, which as a decimal, and this one is exact, it's 0.28. All right. So those are some examples where we're using sine, cosine, and tangent on a triangle to solve for our ratio, both as a fraction and as a decimal. We'll further use that to help us find angle measures and side lengths, but that will be in a further section. Examples 3 and 4 are going to help us learn a little bit more about what happens when you have the sine, cosine, and tangent of 30, 60, and 45 degree angles, which come up quite a bit, so it'll be useful to know that there is the same answer for those angle measures every single time. So the sine of 30 degrees, if we look at this triangle, sine is opposite over hypotenuse. So we have S over 2S. S over 2S. But I have one S on both of these that can cancel out. So my S's cancel out, and that leaves me with 1/2. So the sine of 30 degrees will always be 1/2. Next, let's try the cosine of 30 degrees. So cosine is adjacent over hypotenuse. So I have S square roots of 3 over 2S. S square roots of 3 over 2s. And that, again, I can cancel out those s's, and that leaves me with the square root of 3 over 2. Next, we have the tangent of 30. Tangent of 30 is going to be opposite over adjacent. So I have s over s square roots of 3. Which we can simplify that down to 1 over the square root of 3 because the s's cancel out. But that's not where we're going to stop because we don't want a square root on the bottom of our fraction. So to get that out, I'm going to multiply both the top and the bottom of the fraction by the square root of 3. And when I do that, it gives me that I have the square root of 3 over square root of 3 times the square root of 3 cancels and gives me just 3. So this is equal to the square root of 3 over 3. All right, so for sine of 30 will be 1/2. Cosine of 30, square root of 3 over 2. Tangent of 30, square root of 3 over 3, every time. Next, we have 60 degrees. So the sine of 60 degrees is opposite over hypotenuse. So I have s square roots of 3 over the hypotenuse, which is 2s. We just had that on the other side. We canceled out the s's, and that gave me the square root of 3 over 2. Now we have the cosine of 60 degrees. So the cosine of 60 degrees is equal to the adjacent side over the hypotenuse. So I have s over 2s, which is another repeat. So s over 2s is equal to 1/2 because the s's cancel out. Right. Last but not least, we have tangent of 60. And the tangent of 60 is equal to the opposite over the adjacent. So I have s square roots of 3 over s. And this one is a little different than the other one. So before we had s over s square roots of 3, we got the square root of 3 out of the bottom of the fraction, and that gave us the square root of 3 over 3. This time we have s square roots of 3 over s. And these s's are going to cancel out, and that leaves me with the square root of 3 over 1, which is the same as the square root of 3. If it helps you to think of it as a ratio, then I would write it as the square root of 3 over 1. If you understand that this is a ratio and is over 1, then it is fine to write that as the square root of 3. All right, so sine of 60 is the square root of 3 over 2. Cosine of 60 is 1/2. Tangent of 60 is the square root of 3. And those will be true every single time. So if you'll notice here, the sine of 30 is equal to the cosine of 60, and the cosine of 30 is equal to the sine of 60. So you'll have to make sure that you keep those straight in your head. And we have a chart that will help with that, but we're going to finish with our 45-degree angles first. So if we look at this triangle here, we're going to find sine, cosine, and tangent of a 45-degree angle. And I'm just going to pick this one, and we're going to run with it. So starting with sine, the sine of 45 degrees is equal to the opposite over the hypotenuse. So I have s over s square roots of 2. The s's cancel out, and that leaves me with 1 over the square root of 2. But again, we don't want to leave the square root of 2 on the bottom of my fraction. So I'm going to get that out by multiplying both the top and the bottom of my fraction by the square root of 2. Which, in case you forgot, I'm allowed to do that because it's a fraction rule where you can multiply a fraction by 1 to change for a common denominator. And that's really what I'm doing here. We're just reusing that to help us get the square root out of the bottom of the fraction. So what this does, 1 times the square root of 2 is the square root of 2. The square root of 2 times the square root of 2 is equal to 2. So my final answer is the square root of 2 over 2. The sine of 45 is the square root of 2 over 2. Now let's look at cosine of 45. So cosine is adjacent over hypotenuse. So it's the exact same ratio, s over s square roots of 2, which we just talked about, how the s's cancel out and we get the square root of 2 out of the bottom. So this is automatically the square root of 2 over 2, just like before. Last but not least, we have tangent of 45. Tangent is equal to the opposite over the adjacent. So tangent of 45 is equal to S over S. S over S. Both of those cancel out, leaves us with just 1. S over S is 1. So sine of 45 is the square root of 2 over 2. Cosine of 45, square root of 2 over 2. Tangent of 45, 1. Now we're going to take those in their simplest form, square root of 2 over 2 instead of 1 over the square root of 2. And we're going to put those in a chart on the next page. So if we flip the page, we have this chart here. Sine of 30 is 1/2. Cosine of 30 is the square root of 3 over 2. Tangent of 30 is the square root of 3 over 3. Sine of 45 is the square root of 2 over 2. Cosine of 45 is the square root of 2 over 2. Tangent of 45 is 1. Sine of 60 is square root of 3 over 2. Cosine of 60 is 1/2. Tangent of 60 is the square root of 3 over 1, or just the square root of 3. All right, and I realize that this column is kind of hard to see. The color is difficult to see. I recommend looking at the key that is already posted on the Drive folder attached to the Unit 9 module on Canvas, and you'll have a better view of what we're looking at here. All right, so this is something that you are going to need to know. You're going to need to memorize these. These trig functions happen all the time. You're going to see them a lot. So whenever you're using these, you should be able to quickly pull it out of your memory that the sine of 30 is 1/2, rather than wasting your time solving for it every single time. All right, the last 3 examples in our notes talk about solving for side lengths using our trig functions. Before we do that, we need to know how to solve for, say, 63 degrees, sine of 63 degrees, or maybe cosine of 15 degrees, or tangent of 63 degrees using your calculator. So we're going to skip to a different video where you're going to learn how to plug in those values on your calculator, and then we'll return and continue with these examples. In this video, I'm going to show you how to use the TI-84 Plus graphing calculator to solve for trigonometric ratios with degrees. Because we are using degrees in our angle measures, we need to make sure that our calculator is in degree mode. So I'm going to select the mode button to go into the menu. And in this menu, I need to make sure that instead of radians being highlighted, I need degrees. So I'm going to scroll down, then I'm going to go over to the right, and I'm going to hit enter to select degrees. Now that I have degrees selected, I can go ahead and solve for my trig functions. To do so, I'm going to hit second, then quit to get out of that menu. Then I'm going to type in, let's say we're solving for the sine of 15 degrees. Then I'm going to hit sine, then I'm going to type 15, and then I'm going to close the parenthesis. Then I'm going to hit enter. This tells me that the sine of 15 degrees is equal to 0.2588190451, or approximately 0.26. If I want to solve for the cosine of 15 degrees, I'm going to do much in the same way, but I'm going to hit this cosine button. So I have sine, cosine, and tangent. So cosine, I'd hit 15, and again, close the parenthesis, hit enter, which gives me approximately 0.97. Then I'm going to hit tangent, and if I want tangent of 15 degrees, then I'm going to again type 15, close the parenthesis, hit enter, which gives me that the tangent of 15 is approximately 0.27. Any of those functions, any degrees that I would like to type, it's going to be the same pattern. Select the button for the function you want to use, type in the degrees that you would like to be used, close the parenthesis, hit enter, and it will give you your answer. All right, example 1. Find the length of QR in the figure to the right. So I have a 90-degree angle and I have a 63-degree angle. And because this is a right triangle, I'm going to use a trigonometric function to solve for QR. So if I'm trying to find QR, and that is on the opposite side of the triangle of this 63-degree angle, then I need to use a trig function that uses the opposite side. And I also need to use a trig function that uses the hypotenuse because I have that measurement. So 63, the opposite in the hypotenuse. That sounds like sine. Sine is opposite over the hypotenuse. Can't be cosine because that's adjacent and we need opposite. It can't be tangent because we don't have the adjacent or the opposite, so those don't work. We have to use sine. So the sine of 63 degrees is equal to QR, that's the side I'm solving for, over the hypotenuse, which is 12.9 centimeters. All right, I'm going to zoom in here now that we have our ratio. We can go through and solve. To get QR by itself, I need to multiply 12.9 out of the bottom of this fraction. So I'm going to multiply both sides by 12.9. And that will give me QR. So in other words, QR is equal to 12.9 times the sine of 63 degrees. So I'm going to plug that all in my calculator right as is. I'm going to pull my calculator onto the screen here a second. So I have checking my mode like we talked about in the video to make sure that I'm in degrees. I'm not, so I'm switching to degrees. I hit enter. I want degrees. Then I'm going to type in 12.9 times the sine of 63, close my parenthesis, hit enter, and that gives me 11.493, which means we're saying that QR is approximately equal to 11.49 centimeters. All right, so to reiterate, we looked at what we had, we looked at what we were trying to solve. We figured out which trig function used those pieces. Then we plugged it into our formula. The sine of some angle in degrees is equal to the opposite side over the hypotenuse. Then we did some algebra by multiplying this out from the bottom of our fraction to give us that our side length has to be equal to 12.9 times the sine of 63 degrees. From here, we just typed this right into our calculator. All right, that might be a little confusing, so let's take a look at another example. I'm going to close my calculator and then I'll bring it back up when we need it. All right, so example 2 is asking us to find the length of BC. BC to this angle that we know is 15 degrees, and we're not using the 90-degree angles, by the way. So because we know this angle, and we're trying to solve for BC, then this side is adjacent to 15 degrees. So I need something that's going to be using the adjacent side. So that would be, if I think, Sohcahtoa, cosine and tangent both use adjacent, but sine doesn't. So we're only working with cosine or tangent. Now we have to figure out which of those we want. So the other side that we do know is 10.2, and that is opposite of 15 degrees. So we need a function that is going to involve the opposite and the adjacent. Only one of our functions does that. That's the tangent function. So we think Sohcahtoa, opposite over adjacent. 10.2 is opposite. BC is adjacent. So that is what we're looking for. So to set this up in our formula, I then have that the tangent of 15 degrees is equal to the opposite side, which is 10.2, over the adjacent side, which is BC, and what we're trying to solve for. All right, I'm going to zoom in on this here. I need to get BC by itself. The best way to do this is to get BC out from the bottom of the fraction. So I'm going to start by multiplying both sides by BC. That means that 10.2 is equal to BC times the tangent of 15 degrees. I still need to get BC by itself, so I'm going to divide out the tangent of 15 degrees from both sides. So then I'm going to take a moment and write out that BC is approximately equal to, and from here, this cancels out. what we're typing in our calculator is 10.2 divided by the tangent of 15. So I'm going to pull my calculator back out. I have 10.2 divided by the tangent of 15 is equal to 38.0669. 6 is high enough to round us up, so BC is approximately equal to 38.07. All right, I'm going to close my calculator again. Let's take a look at example 3. All right, so example 3 says to find all missing angles and side lengths. So let's take a look at this triangle here. If we're trying to find all missing side lengths and angles, we need both DE and FD. And I know that angle F is 39 degrees and angle E is 90 degrees, so let's just start with angles. We don't have to do any trig to figure this out. We already know that there's 180 degrees inside of a triangle. 90 of it is already used. That leaves 90 degrees to be split between these two angles. So I have 90 minus 39. So 90 minus 40 would be 50, add 1, so this has to be 51. So angle D is 51 degrees. All right, so now that that's done, I can use my trig functions to solve for my missing sides. And because I have two exact angle measures, I can use either angle to solve for our missing pieces. So I'm going to start with, let's just use our 51 degree angle that we just found just for fun. And I know the opposite side is 20 degrees, and let's solve for our hypotenuse. So my opposite over hypotenuse function is sine. So the sine of 51 degrees will equal 20 over my hypotenuse, which I'll call FD. So the sine of 51 degrees, so the sine of 51 degrees is equal to 20 over FD. All right, now let's go ahead and solve this. So I'm going to do just like I did before. I'm going to multiply FD out from the bottom of the fraction. Then I have FD times sine of 51 degrees is equal to 20. I'm going to divide out the sine of 51 degrees. I'm going to type that right in my calculator. So sine of 20 divided by the sine of 51 is equal to approximately 25.74. So FD is about 25.74. All right, and I'll close my calculator. We'll come back to that in a little bit. All right, so I have about 25.74 for this length. I have one side left to solve for, and if at all possible, I want to avoid using this side length because this is an estimation. This is rounded. This isn't exact. If it was exact, I say go for it. But because it's approximated, then we want to make sure that we're using this 20-meter side instead of this side, as it's going to make our math a little easier. And because of that, and more exact, I'm going to use this side and this side, and it doesn't matter which angle I use again. If I use 39 degrees, then I'm using opposite over adjacent. If I'm using 51 degrees, then I'm using opposite over adjacent. So both of those have to be the tangent function if I'm not using the hypotenuse, because the tangent function is the only one that doesn't use the hypotenuse. Now, the catch here is, do we want to set this up so that we have our variable on top of the fraction, or do we want the variable on the bottom of the fraction? So if we look at our other examples here, when the variable was on top, we just had one simple multiplication, and we had our answer. When we had the variable on the bottom, we had to multiply and then divide. Either is fine, but if I can get the variable to be on the top, then that's what I want to do. So opposite would have to be this side. The opposite is 39, so I'm going to use the tangent of 39 degrees, and that's going to give me this side as my opposite side. Now, if this part's confusing to you, it doesn't really matter as long as you are picking one of these angles and you're using tangent. So I have 39 degrees is what I'm going to use. So tangent of 39 degrees is equal to the opposite, which is DE, over the adjacent, which is 20. Right now I'll zoom in here. I'm going to solve by multiplying out the 20 on both sides, which means that DE is going to be approximately, and we'll pull out our calculator here. So I have, in my calculator, I'm going to type in 20 times the tangent of 39 degrees, which is approximately equal to 16.19. Okay, this is where we're going to stop for today. We'll pick back up and actually solve for our missing angles in our next section.